now that we understand much more about quotient groups, I want to use this video to introduce a big idea. That we're going to try to understand a group G and its structure by understanding its quotient groups. So I want to show you this idea with an example. I'm going to do proposition 21 in section 3.4 of Dumb and Foot. So we moved out of the isomorphism theorems into a new section. I mentioned earlier that later in the course, we're going to prove a result called Cauchy's theorem, which is a partial converse to Lagrange's theorem. It says that if you have a finite group G and P is a prime dividing the order of the group, then G contains an element of order P. So now I want to prove this for the special case where G is a finite abelian group. So let G be a finite abelian group and P be a prime dividing the order of G. Then there exists an element X in G of order P. And this proof begins with a big idea, which is we're going to prove this by induction on the order of G. OK, so like as a base case, if the order of G is just a prime, then we know this is true because we already showed that every group of prime order is cyclic. It has any non-identity element has order P. So what we're going to do is we're going to suppose this result is true for all finite abelian groups of size less than the size of G. And we're somehow going to use that we know this result is true for smaller groups to prove that it's true for G. So let's take an element of G. G has size at least 2, so we can take a non-identity element. So first, what do we do if P divides the order of X? Let's say the order of X is P times some number n. Then it's not difficult to show that the order of X to the n is exactly P. Right? That if it takes raising X to the Pn power to get back to the identity, then if you take X to the n and raise it to the P power, that is X to the Pn, that'll get you back to the identity. And you can work a little bit harder to show that the order of X to the n is exactly P. So let's suppose that P doesn't divide the order of X. Because if P divides the order of X, then we're already done. So let's take n to be the cyclic subgroup generated by X. G is abelian, so n is automatically normal in G. So we can consider the quotient G mod n. OK, so what is true about this quotient? It's a finite abelian group because quotients of abelian groups are automatically abelian. And what's true about the order? Well, the order of the quotient is the order of G divided by the order of n. The order of n is bigger than 1 because X is not the identity. So this is less than the order of G. What else is true about this order? Well, P is a prime that divides the order of G. And the order of X, P does not divide the order of X. So P does not divide the order of n. So that means that this same prime P that we started with up here divides the order of this quotient. OK, so now the induction hypothesis says that G mod n, that's a finite abelian group of size less than the size of G, and P is a prime dividing its order. So by hypothesis, there's some element, let's say y bar in G mod n, which we can write as the left coset of n containing some element y. And we know that the order of y bar is equal to P. So I'm going to pause and erase. We're going to work with this element y bar, which gives this element y in G, and somehow try to combine what we know about what's going on in G mod n to produce an element, maybe not of order P, but whose order is divisible by P in this larger group G. Let's finish this proof. So where are we? We have found this element y bar in G mod n that has order P. OK, so y bar is equal to the left coset of n containing y. So what are some things that are true about this element y? Well, y is not in n. If y were in n, then y bar, the left coset of n containing y, would be the identity, would be the left coset of n containing 1. So that would have order 1 in G mod n, and it doesn't. We know it has order p. But y bar to the p is the identity in G mod n. So y bar to the p is this coset yn to the p, which is the left coset of n containing y to the p. So that means y to the p is in n. OK, so what does that mean? The cyclic subgroup generated by y to the p is contained in n. But the cyclic subgroup generated by y is not contained in n, is actually just is bigger. So the order of y to the p has to be less than the order of y. What does that tell you? Well, we've taken y, we've raised it to the pth power, and the order has gone down. That means that p has to divide the order of y. So you can think about that and try to prove it. This is the second part of proposition 5 in section 2.3. I don't think I proved that earlier in the lecture where we talked more about cyclic groups. So it's a little exercise, or you can look it up. But now where are we? So we have an element y in G. And we know that p divides the order of y. And now we're just back in this case that we did before, where we had some element in G that was not the identity, and p divided its order. You write the order as p times something, and you take that element to the something. Now that has order p. So that's the end of the proof. And what happened here? So what was like the big idea in running this argument was that if we knew enough about our subgroup n of G and about the quotient G mod n, then we could combine this information together to say something about the larger group G. And we'll see more of this in the next video.